Okay. Okay, so let's switch to English as you asked, and that was your own choice. Let's, okay, it will take me a few minutes to do a mental transition, but it will work eventually. So points of singularities. So last time we only briefly mentioned that points of singularities. Singularities. And okay, so there are several divisions into different groups, different classifications. But the first classification is to divide singularity into isolated singularity and non-isolated singularity, and I'll explain what it means. So there are isolated singularities. And obviously there are and another group is non-isolated singularities. Okay, so what do we mean by isolated singularities? So let me discuss only isolated singularities today. I will not be talking about non-isolating singularities. We'll discuss them later. So what are isolated singularities? So let's imagine that we have a domain D. So that's the domain D in the complex plane C. And let's consider some point W inside the domain. And let's discuss a function f. So it's a complex function f. Is a complex differentiable function. For all points z inside D, except point W. So it means excluding W, D. So it means all points in D excluding point W. Okay, so point W is called what's the name for it? Removable singularity. Removable singularity. If there is a finite limit f of z, limit z approaches W. If such a limit exists and it's finite, then W is a removable singularity. Example, function f of z equal so as you can obviously see, there is a limit z goes to 0, f of z goes to 1. So it means that the point W equals 0 is a removable singularity of this function. So there is a function f of z. Z equals 0 is obviously a special point. You cannot tell what is the value of fz at z equals 0 because you need to divide two functions. Each of them approaches 0. So you cannot divide them algebraically, but nevertheless, there is a well-defined limit of this function. You can define its value at 0 by looking at the limit of this expression, and the limit of this expression exists, and it's equal to 1. So point z equals 0 is a removable singularity of the function sine z over z. Okay, so removable singularities are very, very simple. Then next type of singularities are called pole singularities. So the point W is a pole if there is an infinite limit of function f of z. So f of z as z approaches W approaches a point that we call infinity. And if this is the case, this limit exists and it's equal to infinity, then we call the point W a pole of the function f of z in the complex plane. Examples. F of z is equal to 1 over z. F of z is equal to z over z minus 1 square. F of z equal 1 over z cubed, and so on. So for this case, z equals 0 is a point of pole. In this case, z equals 1 is a point of pole. In this case, z equals 0 is point of pole, and so on. You can easily invent as many functions with poles, with pole-like singularities. Are we happy? Do we have any questions?
כאילו, אנחנו רק עושים הצגה של הנקודות עכשיו, נכון?
We only discuss the singular points.
But not how to solve them.
Well, not how they influence integrals yet. Yes. Okay. And finally, there is last time of isolated singularity, and it's called essential singularity. So what is essential singularity? As you can guess, the point W is the point of essential singularity if there is no limit at this point. So the point W is an essential singularity if
אתה יכול בבקשה רק להזיז את התמונות, כן?
אתה יכול ללחוץ שם במינוס וזה ימזער את זה גם ככה?
Okay. So the point W is an essential singularity if there is no limit. If this limit is ill-defined. Example of essential singularity, canonical example of essential singularity that everybody likes is the function f of z equal e in the power of 1 over z. Point z equals 0 is an essential singularity for this function. But obviously you can also use f of z equal e in the power of 1 over z squared, would be also essential singularity. Okay. So non-isolated singularities will be discussed later. So these are 3 types of isolated singularities. Now let's try to connect this classification with the materials that we studied previously. So let us discuss there what we can tell about Taylor and Laurent series for different types of singularities. Okay, let's start with removable singularity. Okay, so removable singularity.
סליחה, אתה יכול רק טיפה לעלות למעלה, כי לא הספקתי להעתיק את מה שכתבת באנגלית? תודה רבה.
Okay, can we proceed? So removable singularity. So let's go back and look at our example. So this is our function. It has a removable singularity at the origin. And we can also immediately tell what is the Taylor expansion of this function at the origin. So what is the expansion of this function at the origin? What is the first term?
הפיתוח של הטור, אנחנו מחפשים, אז נמצא 1 חלקי z כפול הטור של הסינוס, אז 1 חלקי z כפול 1 פחות.
How the sinus starts? How the expansion of sinus starts? So let's write it like this. What is the next term?
אז z בשלישית חלקי 3, סרט ועוד z בחמישית.
And here? Okay, so then we open this thing and we get 1 minus z squared. Okay. So there is a well-defined Taylor expansion near the point of removable singularity. So what if you decided to look at it from the perspective of Laurent expansion? If you decided to look at it as a Laurent series, what it would mean that all the coefficient it means that all these coefficients with negative powers, they all are identically equal to 0. So there is no terms that come with negative powers of z minus w. These terms identically vanish. So the conclusion is that all terms with z minus omega in the power n, where n is equal to 0, all such cn's are identically equal to 0. Okay, so it means that if it's expanding around regular singularity, removable singularity, then all negative powers in Laurent expansion are absent, and they are back to normal Taylor series, and there's a perfectly well-defined Taylor expansion near removable singularity. Well, none of us should be surprised. Okay. So how about poles or non-essential singularities? What we call poles. what can we tell about expanding here? Also, let's first of all look back at our example. V of z, say, equal to z times z minus 1 square. We can write it as z minus 1 plus 1 over z minus 1 square. And this will be 1 over z minus 1 square plus 1 over z minus 1. So we clearly see that there are several terms with negative powers of z minus w. In this case, 2 terms. But what is really important, it's a finite number of such terms. So we see here that in this case, singularity is at the point w is equal to 1. And we have c minus 2 equal 1, c minus 1 equal 1, and all other c's being identically equal to 0. So there's a finite number of terms in Laurent expansion with negative powers. In general, for the pole of degree n, there is a finite limit z approaches w, z minus w in the power n, f of z is equal to c minus n. So there is a finite limit for the pole of the order n, and Laurent expansion of the function looks like c minus n z minus w in the power n plus c minus 1 z minus w plus c0 plus c1 z minus w plus. And what is really important here, there is a finite number in parentheses exactly n terms, and maybe a finite or infinite number of terms with positive powers, and from 0 to infinity Cn z minus Wn. So this is how Laurent expansion near the pole looks like. There's a finite number of terms with negative powers, and exactly the number of terms is equal to the degree of the pole. Okay, so here come to the point of essential singularity. Essential removable singularity. Oh, sorry, essential not removable, essential isolated singularity. And as you might have guessed, in case of essential singularity, there will be an infinite number of terms in Laurent expansion. So consider an example.
תוכל בבקשה רק להעלות קצת? לא הספקתי לרשום.
אנחנו יכולים, פיתוח אורנט זה פשוט פיתוח ממינוס אינסוף עד אינסוף של הטור. אני לא הבנתי למה הגבול הוא C של מינוס n, כאילו זה הגדרה, אנחנו הראינו את זה ואני לא זוכרת את זה. זה.
Okay, so I'm looking at this function. So for this example, yeah? So let's discuss this example. So this is the example, and I'm expanding it. So my goal is to write this function Cn z minus w in the power n. That's a definition of Laurent expansion.
Okay.
So we see that there is a point of singularity at w equal 1. So this w in this particular case will be 1. Now I see there are two terms that precisely has the same structure as I'm looking for, z minus 1 and some power. So this term is z minus 1 in the power minus 1. And this term is z minus 1 in the power minus 2.
Okay.
Okay, so I identified that Laurent expansion of this function consists of two terms. One corresponds to n equal minus 1 and another corresponds to n equal minus 2. And they count with coefficients 1.
Okay. Yeah.
Do you want to have more examples of Laurent expansion?
לא, אני חושבת שהבנתי, אנחנו פשוט מפתחים את הפונקציה בשביל לבודד את השברים, לראות איזה מקדמים יוצא, וזהו, זה לא חישוב, זה פשוט הפיתוח האלגברי של זה.
It's a very simple computation. It's a computation, but it's a very simple computation.
Yeah.
Okay, so let's consider function f of z equal to e in the power 1 over z. Near the point is equal to 0. So what I'm going to do, I'm going to play a trick. I'm going to first of all think that 1 over z is some variable x and expand in small x, and then replace this x by 1 over z. So what it means that this expansion will be 1 plus 1 over z plus 1 over 2 factorial z square plus 1 over n factorial 1 over z in the power n plus. So essentially, this expansion is sum 1 plus sum n runs from minus 1 to minus infinity, z in the power minus n over n factorial. Okay, so except the first term in this expansion, all other terms are coming with negative powers of z. So this Laurent expansion never ends, never stops. And this what always happens in the vicinity of the essential singularity.
לא הבנתי.
It goes to plus infinity, right? Like n equals minus 1 to plus infinity. There is no minus factorial.
I'm sorry?
אין לנו פקטוריאל שלילי. הסכום, הסיגמה.
I'm sorry, yeah. You're right. Sorry. Okay, so So this is the main message. If it's an essential singularity, then there are infinitely many terms. Okay, so here it's the right moment to distinguish it with pole-like singularity. So if you remember, for the pole singularity, there was a well-defined limit at the pole, and this limit was infinity. Like I said, in the case of essential singularity, you cannot even define a limit of the function f of z. And there is a strong verification of this. There is a theorem says that not only you cannot define a limit, actually you in the vicinity of essential singularity, function takes all possible values. And so let me formulate it as a theorem. So there's a theorem. Theorem that discusses the behavior of the analytic function near the essential singularity. So what it says that in the vicinity of an essential singularity, function takes all possible values. So it requires all possible values at the complex plane, and one may choose a set of points a sequence essentially, a sequence of points. Let's call them zk. So z1, z2, zk, and so on, such that as k increases, zk approaches w, or k approaching infinity. So schematically, if there's a point w on the complex plane of essential singularity, I can approach this point in many ways. In particular, the claim is I can always choose a sequence of points, z1, z2, zk, that approaches the point w. So they all are in some vicinity, small vicinity of this point. As k increases, they get closer and closer to the point w. And the value of function at this particular sequence approach a value a, where a is any number on the complex plane, in the complex plane. Including infinity. So the logic goes like that. Function f has essential singularity at point w. Then the theorem tells me, choose any number at the complex plane, call it a. In the vicinity of essential singularity, I will be able to construct an infinite series of points such that function f of z has a as its limiting value. Let me show you let me show you this, how it works by example. So let us look at our favorite function with essential singularity f of z equal e in the power 1 over z. And we decided to expand it in Laurent series, z in the power minus n and factorial. So let's choose some values of a, and I show you how to construct this series. So let's start with a equal infinity. Okay, so let me, and the point of singularity w of the function above is w equals 0. So I need to construct an infinite set of points that approach the origin. So let me take z k be 1 over k. So clearly as k increases, I'm approach 0 on the I'm coming to 0 on the real axis. And my spacing becomes smaller and smaller. So obviously f at point zk is equal to e1 over zk, which is equal to e in the power k. Obviously this goes to infinity as k goes to infinity. So if we want to have a series with a limiting value infinity, I constructed such a series for you. Choose now another point. Let's choose point a equals 0. As can we approach 0 as can we construct a series with a limiting value of function approaching 0. The same story again, but this time let me choose zk equal to minus 1 over k. So I'm now approaching 0 again, but from other side. F of zk now equal to e minus k. And obviously this approaches 0 as k approaches infinity. Okay, so these 2 points are settled. Now let me now take a value of a that is not 0, neither infinity. So in this case, let me choose a series of points zk being equal to 1 over 2 pi I k plus logarithm of a, where logarithm is any branch of it. I'm picking any branch of logarithm, and I pick a branch. I constructed this series of points. Now, function f of zk will be exponent of 1 over zk, which means will exponent of 2 pi I k plus logarithm a, and this is equal to a. So we see that there is a series of points that yields any value of the function as its limit near the essential singularity. Okay, so this was main things about isolated singularities. Now let us discuss the connection between singularities, and Cauchy theorem. What can we tell about role of different singularities for Cauchy theorem? So let's assume that there is some domain D with a boundary C. And inside this domain, but not on the boundary, there is a singularity W. And for simplicity, let us for now assume that that's the only point of singularity inside C. Then we can generalize. So let's assume that we want to integrate function along the oriented curve C, function f of z, and W is a singular point of f of z in D. This is our domain D. C is the boundary of the domain. Okay, so now let's see what happens and for different types of singularity. So let's start with removable singularity. So case one, removable singularities, removable singularity. What is the value of the integral above if W is a removable singularity?
אולי לפצל את האינטגרלים?
אפשר להתעלם כי זה נקודה אחת, לא?
So say it again.
אפשר להתעלם we can ignore that type of singularity because it's one point. So
and what is the answer? What would be the answer?
What was the question again?
What is the value of this integral if W is a removable singularity?
Just simply f of 0 because it's zero.
Correct. So how do we know it's a 0? So like we said, this f of z is an analytic function. So I can take a contour of integration and shrink it and make, so I have an integral of f of z, but I can shrink it to the near vicinity of point W, and when I shrink, I can Taylor expand the function f of z around the point f of W. Yeah? It will be just an ordinary Taylor expansion. Now, so let's discuss what happens. And the contour of integration, I can make it as small as I wish. Now, the first term will be just f of W integral along the contour C, dc, but this is in regular contour of integration, just proportional to its length. I take it length to 0, and therefore I get 0. And the same goes with all other terms, they get small. So if singularity is removable, I can really remove it. It does not affect the integral along the contour C. So I can essentially ignore all removable singularities, plain or raw. Okay, so next level of complexity are singularities. So now let's imagine that we have a function f, and function f of z has a pole of degree n. So let's consider function f of z that has a pole of degree n. What can we tell about the integral in this case?
Maybe that it's diverges.
Didn't we say something about the residue of the function?
What did we say about the residue of the function, and what is the residue? What exactly did we say?
If there is a finite number of poles, then this integral is equal to 2 pi I times the sum of times the residue, which is the sum of all the, yeah.
Okay, so let's assume that only one pole right now, just to make life simpler. So let's assume there is only one pole inside this region of integral. In general, you're right, it would be a sum, of course. And then there's a Cauchy theorem that says that there would be, this integral will be equal to the value of the residue of the function f at the pole. And what is the residue of the function that I wrote above? So for this particular expansion, what is the residue of the function f of z?
C1.
More careful.
Oh.
C
minus 1.
C minus 1. Yeah. So for the expression above, that will be 2 pi I C minus 1. So it means that if there is a pole of a degree n, we know that a function is expandable. In the Lorentz series, there would be a term. There would be a term that comes with C minus 1. And this term, and only this term, oops, what happened? Turn on. No, I don't. What? Can I go back? Yeah, and only this term will determine this was z. Only this term will determine the entire integral. So as soon as you have an expansion of the function f of z in Lorentz series around the pole, then we can immediately tell that the value of integral is equal to this. Okay? Good. So then the question is, how do we find it? How do we find the residue of f of double? That's something that we need to find. So once again, we are given function f of z, and we want to compute, in principle, if we have the Lorentz expansion, that there's nothing to find, we just look at the term that comes with 1 over z minus w. But if we don't have such a privilege, how do we compute this coefficient? the only coefficient out of the entire Laurent expansion that we call residual we need to find. How do we compute it? Any ideas?
How do we find the C's, CNs?
Well, in principle, yes, but I think the equation is simpler. How do we find specifically C minus 1?
We take the limit of as Z approaches W of f of Z times Z minus W.
So if we have f of Z times Z minus W, let's see what happens. So we have Z minus W, and this is the whole series, C minus N, Z minus W in the power N, plus C minus N plus 1, Z minus W in the power N minus 1, plus C minus 1, Z minus W, plus C0, plus C1, Z minus W. So we multiply all these terms, so we get C minus N in the power of Z minus N minus 1, plus C minus N plus 1, Z minus W, N minus 2, and so on. C minus 1 plus C0 Z minus W. And if you will try to take a limit, you will get that all these terms below, and the limit would be infinity, unless, of course, the expansion starts with C minus 1. If you have a pole of degree 1, in which case none of these terms would present, then you will be absolutely right. You multiply by Z minus W, then this term will be the only one that survives, and all other terms will vanish.
אז מסדר n זה פשוט כפול, כאילו בחזקת n.
Okay, that's better. So let's compute it. Let's multiply by Z minus W in the power n. And then what, so let me remove this, sorry. Let's see what happens if I multiply by Z in the minus n. So what happens now is C minus n comes with no multiplicative factor. Then we get C minus n plus 1 Z minus W plus, and then we come to C minus 1 times Z minus W in the power n minus 1 plus C0 Z minus W in the power n, and so on. So what next?
הכל מתאפס, נשאר רק C מינוס n, לא?
So remember, we need to extract C minus 1. We need to find a way to compute C minus 1. So if you will take the limit of the expression above, we will get C minus n. We will not get C minus 1. What should we do to get C minus 1 with this expression? What would you do if you need to get a coefficient C minus 1 of this polynomial? How formally?
Just take n equals 1.
Take what?
N. to be 1.
No, you cannot take n to be 1 because it's a function that happens to have a pole of degree, I don't know, 11. You cannot force function to have a pole of different degree. Function has a pole, its degree is given. You only know it's finite. It may be 1023. This expansion is given. All these coefficients are fixed. You only want to extract c minus 1. And you have all the machinery of complex analysis that you know that you can use. How can you formally program the extraction of c minus 1 from this expansion? What can you do?
We take z to w.
If you take limit z to w, you will get all these terms dropped because they will all now vanish. And only c minus n will survive.
תכפול ב-c מינוס 1 ותחלק ב-c מינוס n.
I don't know c minus 1. I need to find c. c's are unknown.
כן, אבל אז אני יכולה לקחת גבול. אם אני עושה כפול, אם אני כופלת את כל הטור הזה עכשיו, אבל אז יצאו לי שני איברים.
You can maybe divide by z minus w to the power of n minus 1.
If I divide it by z minus w, then I'll get a singular term. That c minus n will be now singular. The limit will be now infinity.
אני קצת נאבדתי כבר במה אנחנו מחפשים. אנחנו מחפשים את ההגדרה של c מינוס 1, אנחנו מחפשים איך להוציא את c מינוס 1, לא ממש...
אנחנו מחפשים איך להוציא c מינוס 1.
אוקיי, בסדר.
So what should we do? What are mathematical steps we can take to extract c minus 1 from this expansion?
Take the derivative, maybe, to the power.
How many times?
N minus 1.
N minus 1. So let's see what happens if we now take a derivative n minus 1 times of the expression above, which was, I remind you, z minus w in the power n f of z. So that was our expression. That's the expression above. And now differentiated n minus 1 times. So what do I get? So just differentiate this thing n minus 1 times with respect to z. What would be the first term that survives?
c minus 1.
It will be c minus 1, c minus 1 with the coefficient. What is the coefficient?
N minus 1 factorial?
Correct. And next term will be c0 and factorial z minus w and so on. So if I take a limit z goes to w now, if I take a limit z approaches w now, that here all terms higher than c minus 1 will die. So terms lower than c minus 1 dies because of the derivative, and all terms higher than c minus 1 die because they have a positive powers of z minus w. So when z goes to w, this thing, the right-hand side becomes n minus 1 factorial c minus 1. So the conclusion is that c minus 1 for this function is essentially 1 over n minus 1 factorial limit of z approaching w of the n minus 1 derivative of the function z minus w in the power n f of z. So for the case of a simple pole, just let's make sure that this expansion makes sense. So, and this is, by definition, this is the residuum of function f at point w. That's another name for this coefficient, because it's very important. We given him a name. We called it res of f of w. So let's discuss what it means for simple pole. For a simple pole, residuum f of w. Simple poles means n equal 1 is equal to, so 1 over n factorial, n minus 1 factorial is just 1. It means limit z approaches w. Derivative of the order 0, so there's no derivative, z minus w times f of z. And this is exactly what we have expected. Yeah? Okay, in particular, let's play with it a little bit. In particular, if function f of z can be represented as a fraction of two analytic functions, phi of z and g of z are both analytic, in D. So there's some domain D in the complex plane. There's a point W. And at this point W, what it means that there's a function g of at point W is equal to 0, while function phi of W is not equal to 0. So it means there is a pole of the function f of z at point W. And the degree of 0 of the function g of w determines the degree of pole, of the function f of z. Okay, are you happy with this? Is this clear? Not really? You want some example?
Yes, please.
Okay, so example of this construction. Let's discuss function f of z equal cosine z minus 2 divided by sine z, and our domain will be here. So this is a complex plane. That's the point of origin. And near the point of origin, I've chosen a small circle and I call it C. And this is my domain D. So what are the singularities of the function f of z? At what point? What is the point? Z equals 0 is a point of singularity. Now, how do I know it's a point of singularity? And if it's the point of singularity, what type of singularity it is?
תבדוק את הגבול, כאילו כשזה שואף לנקודה. ואז תראה איזה סוג של גבול אתה מקבל.
פול מדרגה ראשונה, כי אנחנו יכולים לפתח את הסינוס לטור, ואז לקחת את הלימיט of z minus w.
Okay, so let's see what happens what happens if we expand near the point z equals 0, okay? So cosine z minus 2 when z is around 0, it's roughly 1 minus z squared over 2 minus 2. So it's essentially minus 1 minus z squared over 2. Do we agree?
Mm-hmm.
Okay, so sine z is essentially z plus corrections. So what it means that the function f of z is essentially minus 1 divided by z. So near the point of origin, the function f of z behaves as minus 1 divided by z. What it means, what is the residual function f at point 0?
Minus 1.
Equal minus 1, correct. Now let us go back and see what was this example. This example was of the following construction. I took a function f, which is a fraction of two analytic functions, phi and g. In this case, the function phi, what was the function phi in this case? Yeah, so that was the function phi of z, and the function g of z, exactly. So we have two analytic functions. What happens in this case, that at the point z equals 0, analytic function g of 0 has a 0. Therefore, this was a singular point for the function f of z. Because this function has a 0, because function g of 0 has a 0, it means that the function f of z has a pole. Now, 0 of the function g of z was of the first degree. There. Are we on the same page?
בגלל שאנחנו מפתחים את הטור הצד הראשון, כאילו?
Can you ask?
I don't know why it's degree 1.
Oh, because, okay, so we call this function g of z, okay? We have the function g of z, which is sine z, which near the origin is roughly z. So it's a polynomial. So it's a polynomial. So if you write it schematically, it's as a polynomial z minus w, w in this case being 0, it's in the power 1.
Okay.
So it's a 0 of degree 1.
Okay.
It would be z minus w in the power, I don't know, 2. That would be 0 of degree 2. Okay, so now we take an example when function g of z has a 0 of degree 1. The degree of this 0 is 1. Therefore, function f of z has a pole of degree 1. Okay, so how can we compute a residue of the function f of z? So what is the residue of function f of z in this case? We know from general prescription that what we should do, we should multiply the function by z minus w, take this function, and take a limit, sorry, let me take a limit z approaches W. Why am I using it? Because we have proven that this is in general correct for any pole. And now we know that this pole is the first order, is a pole of degree 1. Yeah? So pole of degree 1. So now what does it mean? It means that we need to compute the limit z approaches W of the function z minus W. And here we decided that our function is a fraction of f of z divided by g of z. Okay, so now let's compute this limit. F of z is just an ordinary function. Nothing happens there at the point W. So we just write it as phi of W, sorry. Function g of z, we know it has a 0 there. So when we Taylor expand there, we write g of z is equal to g of W plus g prime z at point W, z minus W, plus high order terms. But we know that g of 0 has a 0 at the point W. So what does it mean? What does it mean about the Taylor expansion? If we know that G0 has 0 at z equal W, what is the first term in the Taylor expansion?
Just 0.
And
then J tag.
Correct. So we end up with J tag at the point W times z minus W, and we have z minus W. They are coming from this guy. So z minus W cancels, and we see that the limit is f at the point W divided by g tag at the point W. And this is precisely what we saw in our example when we have f of z being cosine z minus 2 divided by sine z. So at point 0, the derivative phi of z was cosine z minus 2, and we replace it by 1 minus 2 equal minus 1. And g tag z at the point W was d over dz sine z, which is a cosine z at the point z equals 0, and we replace it by 1. And therefore, we got that the residue of this function was minus 1.
אבל יכלתי גם להגיד שזה בקירוב מינוס 1 חלקי z, ואז אני כופלת את זה ב-z בכל מקרה. מה ההבדל ביניהם? אני עושה z פחות w כפול פי חלקי g. ואמרנו שכשאנחנו ליד האפס, אז g מתנהג כמו z.
It's the same logic. It's not contradictory. It's the same statement. Okay. I'm just reformulating it slightly differently. It's not anything new. But now let me write a function which would be more convenient to think in my way. But let us discuss a function that looks. Now, as an example, let me now consider function f of z, which is this function, cosine z divided by sine z. Let's discuss its poles and its singularities. So where are the singularities of the function f of z are now? What determines the singularities of this function?
Sine of z.
Correct. So the points where sine of z has zeros would be exactly the points of singularity of the function f of z. So in other words, eiz minus e minus iz over 2I has to be equal to 0. What are these points?
N pi.
Okay, let me get there slowly. Or e in the power 2 iz is equal to 1. So it means that 2 iz needs to be equal to 2 pi I, let's call it k. So we got that there are points zk which are equal to pi k, and at these points the function cotangent z has poles. What is the value of residue of this function at this point? Now you're welcome to think in any way you want.
Okay.
So what is the residue of z of cotangents at this point? It's this set of points. So there's a set of points on the complex plane. They all lie on the real axis. There are multiples of pi, and at these points there are poles of the function cotangent. What are the value? What are the residue of the function at this point?
Maybe -1 to the power of k. It's a bit of guess, but
-1 to the power k was a suggestion. And other ideas, suggestions.
I'm thinking of 0.
0. Any more on the short list?
אפשר לעלות עוד קצת למעלה בבקשה? לעלות עוד טיפה למעלה? כן. אולי מינוס k, יהיה לנו -1, ועבור כל נקודה, k פעמים.
Okay, fine. So I'm glad that none of you got it right. So my way of thinking is advantageous, and that's great. Yeah, everybody loves to be right. So let me look at this back. So remember, we have function cotangent z, and that was a function cosine divided by sine, and this function was chosen that its poles are the first degree 0 of sine. So what it means, according to my logic, that I need at points k to get the residue, to find the residue of this function cotangent at these points. I need to take a limit cosine at point of residue, and there put sine z derivative at the point zk, right? That is, now what happens with sine when I differentiate it?
Just get cosine.
You get cosine. And means that the residue is 1. Correct. So if I now choose an integral somewhere on the complex plane that only encompasses the origin but doesn't touch any other poles, what would be the value of the integral over function cotangent z? Exactly. And if I choose a contour of integration that encompasses some other poles, what would be the value of the integral?
Okay.
It will be 2 pi I times the number times the number of poles it encompasses. The number of poles, the number of these points inside this contour of integration. Let us now play with it a little bit, and instead of this function, let's describe another function f of z, which is a hyperbolic tangent of z, which is a hyperbolic cosine divided by hyperbolic sine. Very, very popular function, very useful in physics. Where are the poles of this function and where do they lie in the complex plane? Once again, these are two functions, two analytic functions, phi of z and g of z. So the poles of the function f are zeros of the function g of z.
כש-i z שווה 0? כאילו כש-e ו-i z שווה 0? e ו-i z לא שווה 0.
The beginning was right. So the beginning was where the hyperbolic sine is equal to 0, which means e in the power z minus e in the power minus z is equal to 0, which means that e in the power 2z is equal to 1. And this means that 2z is equal to 2 pi ik, means that z is equal to pi ik. So if you look at the complex plane, where do these points lie? No, look again.
Image.
On the imaginary axis. So they lie here. As opposed to points, so they're multiples of pi, but along the imaginary axis, as opposed to the multiples of pi along the real axis we had in the case of cotangent. Hyperbolic cotangent has its poles along the imaginary axis. So infinitely many points that are multiples of pi along the imaginary axis. Okay, so what is the residue of the function of this function at these points? Yes, you got it by now. It's a value of cosine at the point zk times derivative of the hyperbolic sine at this point, which makes it 1. And if you want to compute an integral that goes along some contour of integration c, what would be the value of integral dz cotangent z along this contour? 2 pi I times the number of poles. Now imagine something more elaborate. Imagine now you repeat the same exercise, but this time you compute an integral dc cotangent z times some function that's called y of z, and we know that function y of z is analytic in C, has no poles whatsoever. What would be the integral now?
Y שווה דבר.
For any y. Okay, let me write the answer and you will tell me if you agree or not. So it'll be y 2 pi sum over n runs from over all the poles. If you label them, and this will be y at the point zn. Was too fast?
כן, אבל זה לא קצת כמו פונקציית דלטה, כאילו אני מקבלת אני אומרת, יוצא לי 1 בנקודה הזאת, אז אני כופלת אותה בערך של הפונקציה בנקודה הזאת.
Yes, but don't confuse it with the delta function. So assume that there are these poles and let's label them. So this will be, let's call this function, this point Z1. I don't like it. How should I? So these are multiples of pi I. So this is pi I times 0. This is pi I times 1. This is pi y times minus 1. Okay. So now let's decide that we have chosen a contour of integration that, I don't know what contour to choose to make it simple. Let's choose the contour of integration that encompasses the entire imaginary axis. And let's integrate this thing with a function y. What would we get? Oh, sorry. Do you agree? Well, assuming that it converges.
So y makes sense?
Yeah. But don't bother with convergence. So if you fix any contour of integration C that it encompasses a finite number, an infinite number of poles here, and you integrate analytic function with the hyperbolic cotan, you get a sum of the residues which will be given equal to the value of the function y at these points. Now the contour C at your disposal. You can take a contour C which encompasses the entire imaginary axis. It will be true. Or you can take a smaller contour C, say the one that only encompasses the point at the origin. So if you choose a green contour, then it will be, then this integral will be equal to 2 pi I times y at the point 0.
And if the integral, if C does not contain the points of pi I k, then this is simply 0. Like if C, the...
Yeah, but it also should not contain any points of singularity of the function y.
Mm-hmm.
So if you've chosen a contour C that goes like this, and there are no points of singularity of the function, how did we call it, y? So assume that y does not have point of, so imagine that the point of singularity y do not lie in this contour as well, then this contour will be zero, this integral will be 0, of course.
But if there are holes, then they just flip sides, right? Like it will be 2 pi I times, well...
it will be determined by poles of the function y then.
Yeah, because they are not necessarily one, like the cotangents one.
They can be anything. But if you're given function y that does not have poles near the imaginary axis, and you integrate this function with the function hyperbolic cotan, then you tell me the contour of integration, and I'm expressing you as a sum of the values of the function y at these poles. Whatever the function y is, the only thing that I need that this function has no poles near the imaginary axis. Yeah.
זה יעבוד ככה, אבל עם כל פונקציה שהרזידו שלה יהיה שווה 1.
זה יעבוד עם כל פונקציה
השארית שלו תהיה שווה 1.
Instead of hyperbolic cotan, you can use any other function that has a residue equal 1. Correct. Correct. It's absolutely correct. Now, you may know that in physics, hyperbolic cotangent is a distribution, is essentially both a Fermi distribution function. So it's a very useful property of this function in statistical physics. When you sum over different expressions in statistical physics, that's how you do it. Okay, I guess I better stop here. I think I gave you a few examples of how we use Cauchy theorem with different types of singularities. We will proceed exploring these ideas next time as well. And I guess in the exercise, you will have more examples of how to use Cauchy theorem for computing integrals, regular real integrals. Okay, I guess that's it. Do you have any more questions? Comments?
Thank you very much, Dima.
You're most welcome.
Thank you, Dima.
So stop recording and